I'm going to talk types of chemical bonds. So we talked about electronegativity, and this really determines what type of bonds we're dealing with. When you look at electronegativity, if you have a high electronegativity difference, that means that you are going to end up with an ionic bond. You're going to transfer that electron. Remember, fluorine is your highest electronegative element out there. Okay, francium is one of the lowest. So when we're looking at electronegativity differences, if this is like a 4 and this is a 0.7, what is the greatest electronegativity difference we can have? 3.3. Okay, so when you're looking at these big electronegativity differences, that is a transfer of electron. Francium will give up its electron to fluorine. By doing that, fluorine has the electron configuration of neon, and francium would end up with the electron configuration of xenon. So that's a transfer. Let me see, do I have the amounts on here? Okay, so we talked about that, how that's going to be pulled off, compare those electronegativity differences. There are what we say is arbitrary cutoffs for polar, nonpolar, and ionic. Okay, so generally speaking, it's nonpolar if it's around 0.5 or less. It's polar if it's between 0.5 and 1.7. A lot of times in text, you'll see 1.67 for that value. And if it's greater than that, then it's typically considered ionic. This is a range, though. Okay, it is a scale. It is, you know, when you get closer to this difference here, it gets more and more characteristic of an ionic compound. The closer you get to this end, it gets more like a nonpolar. Okay, so it's kind of a sliding scale. It's arbitrary. Generally speaking, covalent bonds are between nonmetals and nonmetals. Ionic are typically between a nonmetal and a metal. Okay. When they talk about a dipole moment here, what they mean is an area that is charged. So di means two. You would have two poles, a positive and a negative pole.
You should go to the hospital. Go get that checked out. That's bad.
All right. Ionic, then. Ionic interactions typically, like I said, occur between a metal and a nonmetal. They're going to lose electrons if they're the metal. They gain the electrons if they're the nonmetal. The attraction then is one of these Coulombic attractions or electrostatic attractions. So you've got a positive and a negative being attracted to one another. The further the distance is away, the less that charge is. They're going to form crystals. What that means is ionic substances at room temperature are all solids. They're collectively known as, all ionic solids are collectively known as salts in the chemistry world. So it's not just sodium chloride, it's anything that is formed from an ionic bond. They have high melting and boiling points. That's why when you took that barium chloride and you heated it, the water went away. Water is what kind of compound? Covalent. Okay. Covalent polar. Okay. So it's going to have a lower boiling point. We're able to drive that water off and leave this behind. Our Bunsen burners don't get hot enough to be able to melt this or evaporate it. melt it, much less evaporate it. Does that make sense? They tend to be hard and brittle. So think of like table salt, for example. They conduct electricity when dissolved in a substance. So if they're dissolved, they're going to break apart. So if we have our sodium, it's going to break apart into these ions and float around in that water. Or when they are molten. By molten, we mean melted. And again, I don't have Bunsen burners that can get hot enough to make this happen.
Yeah, maybe we should like invest in it.
They are good insulators as a solid. So you could use them as an insulator if you wished.
Cool.
The next one is metallic. This is metallic bonding is going to be between metal ions. It can be for just one metal, a pure substance, or different types of metals as a mixture called an alloy. So we talked about alloys when we were in regular chem or honors chem, whichever one you took. And alloys, what they do is they heat the metals up, the two different metals up. They mix them together as liquids, and then they cool them back down. So brass, for example, if you have a brass instrument, if it's truly brass, okay, that's how they created that. Bronze is another example. Metallic attractions then are due to metallic cations being attracted to delocalized C of valence electrons. So these electrons are able to move past the atoms and they're able to flow. Flowing electrons is also known as electricity. And if you want to study that more, wait until the very end of this course or take physics. IMF then is going to be stronger when they are smaller metallic cations and when there are more valence electrons. Properties of these metallic compounds, they have luster or shininess. They're malleable, which means you can pound them into thin sheets. They are ductile. Ductile means you can pull them out into wires. They conduct heat and electricity.
Okay.
Your metallic oxides tend to be basic and ionic, and they lose electrons to form cations.
NO.
What does IMF stand for?
Intermolecular forces.
Yay. We were like all together.
That was good.
As a class, everybody.
All right. We have properties of nonpolar and polar covalent molecules. For the most part, this chapter is spending time here. That's pretty much what this unit is on, is covalent. We pretty much said goodbye to the other two at this point, and now we just focus on this. They tend to be non-lustrous, various colors. They're brittle. They can be hard or soft. They're poor conductors. Their non-metallic oxides are acidic and covalent, and they form anions by gaining electrons. All right, so here we go. Place the following bonds in order of increasing polarity, and then classify these substances below as ionic, covalent, or metallic. So you're looking here at electronegativity differences. No, but like this one should be easy, right? Because the electronegativity difference here is what? 0. So this guy is going to get listed first. So he's done. Now we are going to
See, you did drop.
see, you did. All right. Now we're going to look at the differences here. Okay. Carbon and hydrogen. Where are they located? Where is their electronegativity differences? Well, let's go back to our electronegativity chart here. Okay. This is a 4. This is 3.5, 3, 2.5, 2, and hydrogen is 2.1. So if we're looking at carbon hydrogen, what's the electronegativity difference there? 0.4. Okay. So this guy is 0.4. This guy is going to be 2.5 minus 4 is 1.5. And this guy is going to be 1. And this is going to be a metal and a non-metal, so it's going to be higher than the 1.5. Okay, so he's going to be at the very end. And now we need to order these. So CH comes next. So that one's done. That one's done. Now we need to do our CO. And then we need to do our CF. Okay, and then this guy's last. I have them memorized.
It just goes down by 0.5.
I told you guys in regular chem that the ones I wanted you to memorize were fluorine and hydrogen. So if you know fluorine is 4, it just goes down by 0.5 across. And then this guy is 2.1. So you really only have to memorize 2. That one right there and this one. Because the rest of these you can get just by subtraction. Does that make sense? So if you know this one's 4 and this is 2, and then these guys are generally like 0.7 all the way down, like they're 0.6, 0.7, like they're pretty low. As you fan out and go towards this corner, the rest of these just get less and less. You don't have to know exact values. It's just generalizations for down here. But this one, if you know this one and this one, you've got the ones you need to know then. All right, so the next one is what type of bonds we have. So what type of bond is this? What kind of covalent? Nonpolar. We know it's nonpolar because its electronegativity difference is going to be 0. What is this guy? Ionic. We have a metal and a nonmetal. What is this guy? Ionic. Okay. NO. What is NO? It's cold. Yeah, and this is like the electronegativity difference is 0.5. So I would probably call this polar. Like it's right on that fence line. They would never ask you anything that generalized. What about this? Metallic. This guy. So chlorine is right under fluorine. I believe it comes in at about a 3.5. So 3.5 minus, what do they have it with? Nitrogen. So 3.5, again, that's right on that fence. Like, so this is going to be definitely covalent, and I would probably call it polar. What about this? Now, yeah, but this guy, when we look at him, if we are looking at electronegativity differences, the electronegativity differences are 0.4. So this is going to be classified as a nonpolar bond, but you also have to look at the structure of this. Okay? These are all hydrogens. They are symmetrically placed around here. So this is going to be a nonpolar molecule because of that symmetry. And we're going to get into that more as we move through these units. All right, what about aluminum? Metallic. Okay. All right. Any questions on this so far? All right. So that's 2-1. We're going to talk about 2-2, which is intramolecular force and potential energy. Intra means what? Within the molecule. Okay. We do not abbreviate this IMF. Why? Because IMF is inter. Okay. This is intra. So this is within. So if we go back and look at that one that I was just talking about. Oops. Shoot. Hold on. If we go back and look at that, it is this that we're talking about. We're talking about the bonds within the molecule. That is an intramolecular force versus if we had another molecule here, a force that might exist between that and another molecule. Yep, inter is between. So this is an intermolecular force. This is weaker than intra.
Don't they normally do dotted?
Yeah, that's why I did dotted here.
Oh, okay.
Because they're weaker.
They're spotty.
All right, covalent bonds then are bonds between two nonmetals. They're going to share valence electrons. They can be either polar or nonpolar, means that the electrons are shared either unequally, and that would be a polar, or equally, which would be a nonpolar. And what do we use to determine that? Electronegativity, right. We identify it by using a straight line, but we use electronegativity to figure out what it's going to be. Covalent bonds can either be single, double, or triple. And we also have something called resonance structures, which we will get into. Okay, resonance structures just mean that, well, like here, if we had ozone, ozone is this, or ozone can be this. And this is a resonance structure. So part of the time that double bond is here, part of the time the double bond is here. Okay, and of course we're going to have lone pairs of electrons around these, which you're going to have to start getting drawn in.
Genius.
Okay, so you can draw those in over here if you'd like. But at any rate, it's going to spend part of its time here and part of its time here. And that's a resonance structure. And sometimes they will ask you to draw all resonance structures. Yeah.
See, amigo.
You didn't see that? We wouldn't do that.
It's just our group of
Better?
Yes.
Okay, sorry.
I like to classify myself as.
It was testing you.
I'm trying to talk and draw at the same time, and that's not a skill that I've been able to acquire.
That's exclusion.
All right. Covalent bonds occur at the lowest energy state. This is going to happen when the attraction between the nuclei is greatest. So the attraction is the greatest for the shared electrons, but the repulsion between, remember the electrons want to push away from one another. The repulsion between the electrons is the least. If the atoms are too close together, the nuclei will repel because they're two positive charges. If they're too far apart, then they won't stay together. So there's like this sweet spot, okay? This is shown in a graph below. So if we are here and they're too far apart, they won't be attracted to one another. If we try to get them too close together, like they're trying to do here, then they're going to repel because they're like charges. So there is a sweet spot here where they are the most stable. So this is where that would fall. And this is picometers, so very tiny. All right, so again, we get them too close, it doesn't work. So it's kind of like the Three Little Bears. Papa Bear has it too far away. Mama Bear has it too close. Baby Bear has it just right.
Wouldn't the baby bear be the too close one? And then it goes inside?
Oh, I thought Baby Bear had it just right. Okay, this is the just right. This is Baby Bear right here.
No. Because it doesn't work.
It does work.
No.
Then you keep it up.
The baby is the too close. The mom is in the middle.
No,
And the dad is
the
the
mama is
baby.
always too far this way.
No.
Papa is always too
No.
far this way.
No,
Baby's
no,
too
no.
far.
No, the mother is right in this.
No, mom's forge is too cold. Papa's forge is
It's
too
not
high.
the baby.
Baby's is right.
It's not.
Okay, so bond energy then is the energy required when breaking a bond or the energy released when a bond is formed. The magnitude is the same, but the sign is different. So if we are releasing energy, we are forming a bond. When we are breaking a bond, we need to add energy in. And you can kind of think of that like magnets. When you have to pull the magnets apart, it requires energy. So it's kind of like breaking a bond. Versus when you bring the magnets together, they just snap into place. So larger atomic radii increase the bond length. The longer the length, the less the energy, because they're further away. And remember, when they're further away, they don't have as much of an attraction. Increasing the bond order increases the bond energy as there's more electrons involved. Now, we need to go back and talk about this term. We talked about this in honors chem, but we did not talk about it in regular chem. Okay? So, bond order is very easy to figure out. Yeah, let's go back to our ozone.
No, not Vesper structure.
All right.
Oh, no.
So I want to know the bond order here. What I do is I take number of bonds. So I've got 1, 2, 3 bonds divided by bond sites. So I've got 1, 2. So 3 divided by 2 is 1.5. So my bond order for this guy would be 1.5. If we go back and look at this from a few minutes ago, I have 1, 2, 3, 4 bonds divided by 4 bond sites. So my bond order here would be 1. If I look at carbon monoxide, or carbon dioxide, excuse me, carbon dioxide.
Oh, dang.
How many bonds do I have? 4. How many bond sites? 2. My bond order is 2. So bond order is number of bonds divided by number of bond sites. And if you look down here, you can see Like for example, nitrogen, if it's a single bond, is 418, but now we double that bond order, it's now 941. Okay, it's not a direct doubling of the amount. Sometimes it's, it varies, but you can get the idea that as you increase the number of bonds, you're increasing that energy. Okay. All right. Ionic compounds and lattice energy. The energy needed to separate ions in an ionic compound is called their lattice energy. Why do they call it lattice? Well, that is because they're set up as they call it a crystal lattice is what they call it. Okay? Because you have this alternating, and this is in a three-dimensional world, and you're creating kind of this lattice structure from that.
Yeah.
Okay, so it's the energy that's needed to separate these bonds between these different ions. Combining ions, then bringing these back together, will release energy. So lattice energy can be represented using a modification of Coulomb's law, where the energy is proportional to the charges and inversely proportional to the distances between their nuclei. Larger charges, there's going to be more attraction. So you would have, when you had a 2+ charge here, for example, between calcium and oxygen, that's going to be greater than just this right here, which would be a single charge. Smaller radii have more attraction, and so there's more energy required to separate those as well because their nuclei are closer together. All right, the bond energy for our CC double bond here is 614 with a bond length shown here. It is shown on the graph. Sketch the CC bond, and so single bond carbon and triple bond carbon. So sketch those on the line. Huh? This is supposed to be a triple bond. I don't know that it kind of formatted perfectly for you, Ben, but you get the idea. Huh? Where's your ID? Take it with you.
Why?
I will guarantee that you will see one of these on your exam in May. I'd put money on it right now.
As a free response?
I don't know. In some format, multiple choice, free response, you will see a graph like this on that exam. Okay? I would almost put money on it at this point. You see this every year in some fashion. So this is the double bond here. Would the triple bond require more energy or less energy to pull it apart? Okay, so that means that it's going to be over here. Is it going to have, and it's going to be closer together because you've got a triple bond. So when you draw that in, it's going to be on this side. It's going to come down lower than this guy. And then he'll come up here, something like that. So that is my triple bond. And it makes sense then that your single bond would have less. And where is the bottom of it going to be? A little higher. Yep, good. Okay, so it's going to be over here. And it's going to bottom out a little sooner. And then it's going to come up.
Okay.
Okay? So that guy will look something like that.
H, X, H, Y, and H, Z.
All right. One way to identify an unknown substance is to measure the bond length. HX, HY, and HZ were analyzed. and the following graph was created, it was known that it was HI, HCl, and HBr. So we have to match up these unknowns with what they were. What is the difference between these three in terms of structure?
Number of
Occupied energy levels.
Okay, so number of protons. What else is different in their structure? Uh-huh. So the number of energy levels, which one has more?
Iodine.
Okay, so iodine has more, which means how is that going to affect these things? Which one of these things is that going to affect? The distance, right? So HI is going to be further apart. So therefore, which one of these is going to be HI? Z. Okay, so this is going to be HI. What is HY going to be?
HBr.
HBr. Making this HCl. So do you see how I logicked through that?
I did too.
So tonight you have 2-1 and 2-2 to do.
Okay.